Hello.
Hello, sir. How are you?
I'm good, thank you. I hope I'm in good time to join. Yes. So there's five minutes.
Yeah, I think Burman, sir.
Yeah.
Namaste, Burman, sir.
Yeah. So should I just?
Sir, wait for 5 minutes.
Yeah. Do you want to check that everything is okay if I share my screen?
Dr. Burman, sir.
Yeah.
Okay.
So, sir, want to share the screen?
Yes, I'll
Right.
check. Just check.
You can check, sir.
Is that okay?
No,
Not,
it's not yet. Not yet. So you have not made him a host.
no, it's enable for all participants, panelists.
Yeah, okay.
Okay. So
It's okay now. You can
So
just.
select your file. Sir, select your file.
Yeah,
Yes,
yeah,
sir.
yeah.
Yes, sir.
Yes.
Yes, sir. Yes, sir.
okay.
Now it's visible.
Okay. I'll just leave that for a
Yeah.
moment. And so I'll just wait until you tell me to start, okay? So I cannot hear anything, but tell me when you want me to start, please.
I'm waiting for the chairman to join. Just
Okay, yep,
wait for 1 or 2 minutes, then we'll start.
okay.
I welcome all of you in this very important session, that is plenum lecture. Now I request Dr. H.S. Sen to chair this session, and Dr. S.B. Kadekar, who will act as a reporter for this session. Before this hand over the session to our chairman, I like to introduce our today's speaker, Dr. Professor T.J. Flower. He graduated from King's College of London in 1964 and completed his PhD at the University of Nottingham before undertaking postdoctoral research at the University of Illinois. He returned to the University Sussex in UK in 1968, where he began research on the cellular basis of salt tolerance in halophytes, a topic that is interested from throughout his career. Along with Dr. Tony Yo, he conducted extensive research into the salt tolerance of the halophyte, Pseudia maritima, and then his support from the UK government on rice. The work on rice led in collaborations in Pakistan and Central Science and Research Institute in India. After completion of a term as the Dean of the School of Biological Science, he again took up his interest in halophyte, working on development and revision of the database eHallo. Team is the co-author of the 2 books, co-editor of 3 other books, author or co-author of 42 reviews, editor of 6 special issues of the journal, and author and co-author of 190 peer-reviewed papers. Now welcome Professor T.J. Flower for your plenum lecture. Now we request our chairman, if you want to say something in this session, otherwise we request our
welcome, Professor Flowers. Thank you very much for acceding to our request to give this plenum lecture, the first of the series of 11 plenum lectures that we have listed down. And we are very happy to have you here in our midst to advise us with your new concept of eHallo, a database of salt-tolerant plants. Does it help in your research or not? We are keen to hear you on this new concept that you want to introduce. Thank you very much. Professor Flowers, please.
Thank you very much, Dr. Sen, and for the introduction. I hope everybody can hear me. I'm going to say a few words about this database, the eHallo, and about how it can be used. So I'll talk generally about halophytes to start with. I'll mention then a database called Hallof, which was produced by James Aronson. I'll then describe eHallo. It's something about its origins, its development, and the current database. And then I'll say something about how Hallof can be used and is useful. The background to this is well known, in fact. There's a huge volume of water on the planet. Of course, most of it is seawater. And the problem is, for agriculture and for humankind, most plants are killed by salt water and rely on distillation, that's evaporation, and rainfall for their water supply. So we also know that rising sea levels associated with climate change will probably cause overtopping of coastal defences and potentially generate problems for coastal agriculture, simply because most plants, most crop plants, are salt sensitive. However, we do know, we do know that some plants are salt tolerant. These range from trees, here in the bottom right, to annual species. They occur across from the tropics to the northern latitudes, although trees are only found in tropical areas. They can grow in seawater, or here in northern India in very dry, arid, alkaline soils. So halophytes are plants that grow naturally in saline habitats. And there's a dividing line between what we can call halophytes and non-halophytes, or glycophytes. Now, this dividing line's arbitrary because there's a continuous range of tolerance amongst plants. But it's been set between about 80 and 200 millimolar salt. So halophytes have been called plants that survive in 80 millimolar and above, or 200 millimolar and above, somewhere in between. Just for comparison, seawater is about 500 millimolar sodium chloride. So how would you know if a plant is a halophyte? Well, you can check the natural habitat for the salinity, or you could grow the plants in some sort of culture system. If you're going to use natural habitats, then there are problems with assessing the salinity because it may vary seasonally, and it may vary spatially between and underneath plants. So that has to be borne in mind. And of course, if you're going to grow plants in culture systems, then very often it's quite hard to mimic natural daylight radiation, and also to get the temperature and humidity regimes to mimic those found in natural conditions. Under natural conditions, salinity can be quite variable in saline sites. It's interesting that the concentration of salt, even in salt marshes, even in northern Canada, generally doesn't seem to drop below about 100 millimolar. But of course, it can be extremely high, more than 2 molar, where the climate is very dry. So we're looking at, under natural salt marshes, salt concentrations of 200 millimolar or more. Well, in 1989, James Aronson, he was a French scientist who was working in Israel at the time, published a database of salt-tolerant plants. He called it Halof, and he included in this database, this list of plants, he included all those with a known or presumed tolerance to an electrical conductivity measuring about 7.8 decisiemens per meter during significant parts of the plant's life. So this is about 80 millimolar sodium chloride. And you should realize that the database was compiled for anyone growing or planning to grow half-ice. So it's got an agricultural context. This is at a time when saline agriculture had quite a deal of prominence, and people from California to Israel were looking at how to grow plants in saline environments. James Aronson's database was built on a list published earlier by Peter Moody, and she looked for plants growing in naturally saline habitats, found about 550 species. James Aronson's list, because it had a lower salinity for inclusion, had about 1,560 species, 550 genera, 117 families. But this was a printed database. It's a book, and so it has limited use in terms of simple searching, compiling lists. So in the early parts of this century, I had the idea that we should turn Halof into an electronic format. We did this firstly by scanning all the pages of Halof with permission, of course, from James Aronson, converting it into Excel with text recognition, then into Microsoft Access, and then with the help of Sarah Flynn, who was working at the at the Millennium Seed Bank, which is part of the Royal Botanic Gardens in Kew, she added it into the seed information database of this Millennium Seed Bank. And a version is still there. Well, from the period from about 2009 to 2014, I chaired a cost action, which is a European grant which enables collaboration between laboratories. Over this period, the Microsoft Access database was converted to a web-based format, eHalof, and we published this in 2016. Joachim Santos, the first author, is the person who wrote most of the code for eHalof. And eHalof is now hosted on the University of Sussex website, and it can easily be found, if you've not seen it, by Googling eHalof, and it will come up and you can look at it. When you when you do this, I'll show you in a moment how it's rather simple to use. So in converting Halof to eHalof, we had to revise all the names against the plant list and then Plants of the World Online. Taxonomists are in the habit of revising names, and it's quite a challenge to keep up with them. So we did use first the plant list, but that stopped being updated, and now we use Q's Plants of the World Online. We've also checked and are continuing to check all the original records against the Web of Science. We, and I say the we is Dr. Mohammed Al-Azawi and myself, are also checking new records that were listed in another listing by Menzel and Leith. So we're checking all these against the Web of Science, and we're quite rigorous in terms of retaining or including new records, that there has to be published data on the salt tolerance. It might be that it's well established that plants grow in the salt marsh, or that there have been records of tests of growing the plants in culture. So all the records that we've got so far, and we haven't finished checking yet, but all the records that are there show that the plants do grow in saline conditions. There is published data. So when you log on to eHalof, this is what it looks like. I had thought at one time that I could do a live demonstration, but I was then nervous of the technology over this distance. So there are a series of stills images of what happens. The database has a number of drop-down menus. This is the home page. The plant database is a search engine, references. That takes you to a searchable list of bibliography. And there are about 11,500 references on halophytes in the database. Links can take you to other information, for instance, mangroves, news. Well, you can see some news on the bottom of this. About simply tells you the history of this, and using eHalof is basically what I'm going to say now. There's another search engine listed at the top right, which you can put in the name of the species. The login allows people to register and log in, and that's useful if you, well, necessary if you want to edit the data. So if I look at the plant database and click on that, then there are three searches that are available on that. One called stats, one list plants, and one search plant name. The stats tells you how many species there are in each of the families, and the families of flowering plants with halophytes are arranged pictorially in order of this number of species. So large square for a family with a large number of plants. If you take the mouse and fly over one of the headings, it'll tell you how many species there are in that family. Then there are two other options, one called list plants and one called search plant name. I'm going to deal with the search plant name first. And for instance, so if I click on search plant name, and then in the search in the box, write Salicornia brachiata, and then click on the link that comes up, I'll find information about Salicornia brachiata. And then you can do that for any one of the species. You get a table which shows you all the information that we have in the database about that plant. I should say that in the original Halloff database, James Aronson had listed the plant type, the life form, the maximum salinity tolerated, something about its photosynthetic pathway, the economic uses, and where the plants were found. Now, going from Halloff to E-Halloff, we have added data on antioxidants, on secondary metabolites, molecular data, compatible solids, and the habitat. And we've also listed in here whether there are publications on ecotypes and germination, the presence or absence of salt glands, microbial interactions, microbial and the mycorrhizal status, as well as bioremediation. And on the left-hand panel of this figure, you can see the sort of information that you can obtain for each of these categories. Now that, I mentioned now list plants because this lets you search for those individual categories. So if you click on the list plants drop down, then you get a series of boxes which you can enter, for instance, the family, the life form, salt glands, antioxidants, etc. You can use the drop-down menu to put in information for any of these categories. Here I'm illustrating this with putting plant type hydrohalophyte and the life form tree. So these are trees that will be tolerant of salinity in a wet environment. I've left select families blank because that means we'll get all the families with hydrohalophytes and trees, and all the others are all values. So when I click on this link, then I will have here the families being all families, plant type hydrohalophyte, life form tree, and I'll get a list of species. Now it's possible to output that list into a file that can be opened by Excel. So there's a little place where you can click and you will get this box that comes up on the right hand side where you can export from the database and download a spreadsheet. You can say whether you want it the fields separated by semicolons, commas or tabs, and you get an output, something of this sort. And then you can separate using text to columns. You can separate all the data and analyze it as you might ever want to in Excel. So that basically is eHalloff. It's relatively simple to use to get output. In fact, so now what I want to say is a little bit about using eHalloff and how it might be useful. So, for instance, firstly, how many halophytes are there? Well, it clearly depends on the definition. Vernon Chapman used a rather low salt concentration, about 86 millimolar. James Aronson's already seen about 80 millimolar. And in 2008, Tim Colmer and I decided that we wanted to try to separate crop plants from plants which grew naturally under saline conditions, where the salt probably was around 200 millimolar salt. And for the purposes of this talk, I should call these euhalophytes. So if currently in eHalloff, there are about 1,200 species of salt-tolerant plants. That is plants that will tolerate 80 millimolar salt or more. 300 or so less than Aronson, because we've removed a lot because we were not convinced of the published information. They may well be salt tolerant, but there isn't published support for that inclusion. The Amaranthaceae have more than any other family. Poaceae, big family, have about half the number, and so on and so forth. We can also use E. Halof to put in the criteria of plants that grow in seawater or in salt concentrations more than 200 millimolar. And then we get the number of what I've called euhalophytes plants, which are the more tolerant, and there are around 600 species. Now, the Amaranthaceae are still clearly the most the prevalent family, but of course, some of these mangrove families like Rhizophораceae and these seagrasses appear now in the top ranks. And of course, if you look in the seagrasses, then nearly all of those grow in seawater. There are a few other examples I'll illustrate of how it might be useful for people to get information from the Halof. For instance, you might be interested in the number of salt-tolerant trees, or the number of trees that survive in seawater, or plants with salt glands, or the phylogeny of these salt-tolerant plants. Well, the number of trees turns out to be about 200 species. The trees that survive in seawater, mangroves, we have about 58 species and 22 families. There are 153 species with salt glands. And if we want to look at the phylogeny, then about 10 years ago, I collaborated with Lyndall Broman, who is an evolutionary biologist who works at the University of Canberra. She had previously worked at the University of Sussex, to plot the distribution of clades containing euhalophytes. And we found something similar to I'd already found back in 1977, that halophytes are scattered through the families of flowering plants. They occur right across these orders. The same occurs with plants that have salt glands, whether they're the multicellular glands of the Plumbaginaceae or the unicellular glands, bicellular glands of the Poaceae. Then again, these presence of salt glands are scattered across the families of flowering plants. And this distribution suggests that salt glands, as a mechanism of tolerance, has evolved independently several times. And the same is true of salt tolerance itself, that it seems to have appeared multiple times. We don't know, of course, whether each family having halophytes is a single origin or multiple origins. And if a clade contains both halophytes and non-halophytes, we can't be sure whether tolerance was gained many times or not. And to me, this is, well, it was surprising as there would be so many origins of salt tolerance, and because the traits physiologically and biochemically complex, and so the fact that there aren't many species halophytes are rare, and even if you take the broader definition of 80 million, there are only 0.3% of the world's vascular plants that are salt tolerant. So these are rare plants. And E. halophyte does list these. There are over 11,500 references. And all this data is freely available. And so it would be really very helpful if people with information about these salt tolerance could add them to eHalof. And hopefully, in the long run, we can avoid scenes like this where salinity has had a devastating effect on the landscape. Thank you very much for listening. Thank you.
Thank you very much, sir. Please stop sharing this screen. Yeah, thank you.
Okay.
Now we request Professor Sen for his remarks.
Sir, you are muted. Sir, unmute, please.
Excellent concept that we have been trying to propagate for quite some time. In fact, I'm sure that this concept will gain ground in course of time. And I will first ask for one or two questions, if there is anything that Professor Flowers may be pleased to discuss and answer. Professor Das, if you are here.
Yes, I didn't hear. It just went silent. My screen went. I lost the sound.
So Dr. Sarangi is raising his hand. Dr. Saroj Sanyal also.
I have no sound again.
Yeah, sir, my question is, halophytes are the naturally occurring plants. Now with increased salinity, there is a requirement for cultivation of halophytes. In your e-halophyte, whether we will get some information on the recent cultivation practices of some of the halophytes. Is it there in the halophyte database?
Sorry, I didn't hear all that question. I don't know, Dr. Sen, if you could.
Yeah, sir. Halophytes are the naturally occurring salt-tolerant, salt-loving plants, and of late, due to increase in the salinity, now there is demand for cultivation of some of these halophytes. Whether we can have some information on the cultivation practices of these halophytes in the eHalof database.
Right. So we do list in eHalof economic uses, which is something that James Aronson also listed. And so there is information there about whether the plants are useful for instance, as ornamentals, as the source of pharmaceuticals or wood or whatever, or vegetables. So there is some information there. It's slightly limited by the format that James Aronson used, which is a little database called Cepasal, which is describes the economic uses of plants. But yes, there is information in eHalof about economic use.
Yes, thank you.
Any more question, please?
May I put forward a question to or comment to Professor Flowers?
Yes, yes, please.
First of all, flowers, that's an excellent compilation of the data that you have been working on for a long, long time. I have a, I'm just would like to know whether you're also planning to put forward the genomic data that have been available for some of the halophytes now into this database.
Yes, it's a slightly long story, but I had planned to do this some years ago, but the question really we're facing, right, I put in a grant application to our UK, but BBSRC, but it wasn't funded. So to do just that. So the question now really is how best to link those molecular databases to eHalof. And I do have a small grant which is running at the moment where we are reprogramming eHalof. Hopefully, we will be able to provide links to the genomic data. At the moment, what we have is just reference to papers, but we're trying to work out the best way of linking to these other big databases, genomic, proteomic, and databases.
Hello. Hello.
Most of the things have been done with the not only the sequences but also some microarray data are available, some proteomic data are available, and there have been reason to believe that some of the proteins are allelic different forms of the salt-tolerant version. So that will give you an extremely important component to the database that you have made so far. I believe this will give you an extremely good upliftment of the HALOF in terms of the repository of knowledge about the halophytes.
Yes, I agree. It's quite important to try to do that. We have looked recently into transgenic plants and trying to see whether the using genes from halophytes was more effective in raising the tolerance of crop plants than the same genes from other from non-halophytes. And we couldn't find any difference, but there clearly are some regulatory processes going on in halophytes that are different and perhaps related to protein synthesis and helicases, for instance, and to signaling molecules. So I think that will be really interesting to do. Thank you.
Thank you.
There was one question from
I
think this was not directed to Professor Flowers directly. I think we have to close it down. Professor Flowers, thank you very much, because we have got another plenum lecture from the director of World Fish waiting here. So
Yes.
we are already overshot the time. So thank you very much for your kind presence and your deliberations and participation in this program. Thank you so much.
Thank you.
Wish you all the best.
Thank you.
Wish you all the best, sir.
Yeah.
Thank you.
Pleasure.
Sir, now we can start our second plenum lecture. For that, I invite Dr. M.B. Gupta, former Assistant Director General, International Relations and Partnership, World Fish Center, Malaysia, as the chairman of the session. In this session, the plenum lecture will be delivered by Dr. Michael Phillips on the future of fish agro-food system. And I request Dr. S.K. Das to record the proceedings of the session. He is the principal scientist of Central Institute of Water Aquaculture, Kaptip Center. Dr. M.B. Gupta, please.
Dr. Gupta, kindly unmute your mic.
Yeah. Okay. Thank you very much. Thank you all and good evening. I would like to introduce today's plenum lecture by Dr. Michael Phillips. He is fondly called by all of us as Mike. He is the director of the CGIAR research program on fish agri-food systems. Recognized as a global leader in aquaculture and agri-food system research, Michael joined World Fish Center in 2008, where he has since developed a wide portfolio of research on aquaculture and fisheries. Previously, he served as program manager at the Network of Aquaculture Centers in Asia Pacific, or NACA, where he managed the organization's aquaculture research and development programs. Michael holds a PhD in aquaculture and fish behavior from the University of Stirling and a BS in biological sciences from University of Lancaster. In his current role, he leads the CGIAR's global program on fish agri-food system that aims to enhance the sustainability, productivity, and resilience of fish agri-food systems globally to reduce poverty, enhance food and nutrition security, and improve natural resource systems. Dr. Michael Phillips will be talking to us on the future of fish agri-food system. Now I invite Dr. Michael Phillips to give his talk.
Thank you so much, Professor Gupta. Very nice to see you after a long time. Okay, thank you for the introduction, and thank you, Dr. Sen, also for the opportunity to join the webinar. So I'm going to attempt to share screen. Just please bear with me whilst I do that. Okay, here we go. Is that visible?
Yes, sir.
All right, thank you. So I really appreciate the opportunity to participate in the webinar today, and thank you to the organizers. What I would like to do during this 20-30 minutes is to give a high-level overview of some of the work and the direction and emerging results from the research for development program on fish agri-food systems. And this is one of the global research programs of the CGIAR, which is a global agricultural research network, including with some significant activities in India. Anyway, appreciate the opportunity. So let me just start and move to the first main slide. Okay. So, and this is the slide that has the most writing on. So don't worry, they're not all going to have so much writing on. But why do we think that, or why is it that fish and more broadly aquatic foods, and we're quite interested to listen to the Halifax presentation before that, because there's a very interesting another area of food production that deserves more attention. But why are fish and aquatic foods important globally? Production, we know there's high production. We know that fisheries and aquaculture produce around 170 million plus tons. We know that aquaculture, the farming of fish, is still one of the world's fastest growing food production sector, but growing fast to meet the growing demand for fish globally. And now about half of the fish or aquatic foods that we eat comes from farming or aquaculture. We're increasingly recognizing the importance of fish and aquatic foods in health and nutrition. Over 1 billion people are dependent on aquatic foods as the primary animal source food, and many more. It makes a significant part of the diet. And increasingly, we're recognizing that the micronutrients in fish are of special importance to human health and nutrition. It's important for many livelihoods. A high proportion of women in many of the value chains, the fish food systems that are operating in such diverse ways around the world. And we're increasingly realizing that this can be a very climate smart food, both low carbon production, and there's an echo coming through, and a means of adapting, particularly in coastal areas, to the challenges of sea level rise, salinization, etc. The value is about $1 trillion that globally in terms of production and trade and retailing, and it's fish and aquatic foods are one of the world's most traded agricultural products, so vast movements around the world, and it's a growing sector. So it provides many new opportunities for jobs, employment, particularly across Asia, Africa, and the Pacific. Could someone switch the microphone, please? There's an echo coming through. Thanks. So briefly on the research program. The research program on fish agri-food systems, 5-year program with these overall objectives, basically looking at both aquaculture and the particularly species that are important in Asia and Africa. So focus on tilapia, carp, inland systems, and fisheries, small-scale fisheries in particular, both coastal and inland. And looking at ways, one, to uncover and understand the values of these systems, and also ways of sustaining and sustainable growth of these systems. This is a partnership program, many partners involved, stretching across quite a number of countries from the Pacific through to Africa, and increasingly an active program in India, particularly in the state of Odisha, and now growing elsewhere, but very much a partnership, working in partnership mode from local communities, state governments, national ministries of fisheries, through to global organizations such as FAO. The focus on sustainable aquaculture, or a focus on sustainable aquaculture, essentially recognizing that aquaculture needs to grow by, depending on the country, globally at least 30% in terms of supplies by 2030, and for many countries substantially more to meet the demand for fish. The program focused principally on sustainable intensification and extending knowledge in aquaculture across Asia, Africa, and the Pacific, focusing on application of science in genetics, health and feed management, aquaculture systems, and delivery and uptake of technology. Principally working in Southeast Asia and South Asia, increasingly focused on Sub-Saharan Africa, where there is, and likely to remain without significant investment, substantial shortfalls of fish and aquatic foods. At the same time, the program gave special attention, or gives special attention to sustaining small-scale fisheries. These are particularly hidden in many policies, statistics, but critically important for the livelihoods and nutrition of millions of people. The program worked on improving co-management, integration of fisheries into multifunctional landscapes. That's looking at where fisheries fits into the broader water and land management and seeking management solutions that allow both water and fish to agriculture and fisheries to thrive in a complementary way, and highlighting the hidden values of fish and a special emphasis on nutritional outcomes and nutritional importance of small-scale fisheries. With a strong thread of cross-cutting work going through the program on gender and developing a number of tools for seeking to transform and understand and transform and support the role of women in fisheries and aquaculture, seeking ways in which employment of youth can be enhanced in growing aquaculture sectors, working closely with a number of partners to enhance capacity of many people at different levels, and increasingly focusing on the role of fisheries and aquaculture in enhancing the resilience of our fish food system, agri-food system, to the challenges of climate change. And in 2020, we were, like so many others, also shifting our programs to assess and support in our national partners in responding to the COVID-19 pandemic, and both sort of high-level assessments of the impacts on COVID-19 on fish agri-food systems, and direct support to local governments, state governments, and national policies, research community to address the challenges of the pandemic. And that work is still ongoing. As we progressed in the program, we increasingly started to take a food system approach. And this is a rather complicated diagram in a way but a classic diagram of the food system, stretching from production through to outcomes and nutrition and health outcomes. So how do you engage with, support a system, a food system, to connect sustainable production through to healthy populations? And so our work increasingly took this systems approach, looking not only at production, exploring how different drivers influence the production and supply of food, understanding more about consumers and diets, seeking ultimately to ensure that the aquaculture and fisheries supply delivers the best in terms of nutrition and health outcomes, also taking account, of course, of social, economic, and environmental impacts as well. So increasingly taking this framework for our analysis, our research into the food system, not just focusing on production where we traditionally work, but the food environment through to the outcomes. I'd like to now just talk through some of the emerging messages from the program that we or the teams consider are important for the future of fish and aquatic agri-food systems. Firstly, there's a tremendous opportunity to ensure a greater role of fish and aquatic foods in policies and investments that are directed towards food systems. We often focus very much on what's happening within our sector, within the fisheries sector, within the Ministry of Fisheries, the Department of Fisheries. But to enhance the impact that fish and aquatic foods can have as a highly nutritious product, we need to make sure that fish and aquatic foods are in the food policies. Of course, we also need to ensure that they're in other policies where that relates to the overall productivity, sustainability, and impact of fisheries and aquaculture. So one of our emerging messages is really to engage more widely and seek to influence and ensure that fish and aquatic food are in those bigger policies that are important for our populations. We're also realizing that there needs to be also a focus on diversity. And that diversity stretches from the production system through to the plate. And maintaining diversity in the production systems, and this is some work that was had explored in more detail the influence of diversity on production, resilience to climate, and nutrition within the Mekong region. And so ensuring diversity in the production systems helps to enhance and secure diversity of the outcomes for the many people involved, as well as enhancing overall resilience to the changes occurring. The third area that we highlight is for many, the understanding or the capture of information in statistics, in policies, is still limited. And so we have worked very closely with FAO and a diverse range of partners at different levels to illuminate the hidden value of small-scale fisheries. One of the key messages coming through from that work is the importance of improving understanding, ensuring policies and investments include the underreported and hidden components of the agri-food system, including small-scale fisheries and including women and children who are often highly dependent on agri-food systems, but often unrecognized in many policies, investments, and statistics. So an important area for change. Fourthly, a greater focus on value chains and tremendous opportunities to improve the value chains, the environments, the policy environments, the investment environments that takes fish from the production side through to the consumer. And particularly one to highlight is the opportunity for greater use of loss and waste. And the bottom right-hand side is obviously fish bones. We increasingly understand that there are amazing opportunities for better use of byproducts, many nutrients lost in fish as they're filleted, and significant opportunities to reduce food loss and waste and create nutritious products. So an important emerging area for attention. The fifth area that we highlight is the importance of identifying and managing the trade-offs within agri-food system and with other sectors, such in the use of water, the use of feed ingredients. And one of the controversial areas, of course, is using fisheries to feed fish in aquaculture. We need to recognize the trade-offs that are occurring in the sector and look at ways to optimize, encourage the most efficient and effective use within the fish agri-food system. We work very closely with our partner institute, the International Water Management Institute, as well as FAO, to try and raise the profile of fisheries within overall water management, because the decision by water planners, managers, and engineers on how water is managed for agriculture and other uses has a tremendous influence on the aquaculture and fisheries and sectors. So very important opportunities to better understand the trade-offs within the sector, with other sectors, and to better optimize the use, productivity, and outcomes from such resources. The sixth area is to better understand and manage external risks. COVID-19 is a classic example. Climate risks are very significant for fisheries and aquaculture and the people that depend on fisheries and fish and aquatic foods. We've worked closely with a number of research centers to better understand the climate risks to aquatic food systems and the outcomes that they deliver. And not surprisingly, many countries in Africa and Asia are significantly vulnerable to climate risks, and these need more attention. Indeed, aquatic foods, aquatic systems are often missing from the big climate investments that are made, but we need to increasingly ensure that they are not, and that our work within agri-food systems responds to the changing climate and some of the opportunities that provides as well. The social and economic inclusion has come through very strongly from the research, and ensuring that in policy and investments that the needs of the most vulnerable are addressed. So a little bit like the hidden values, but again, giving special emphasis within fish agri-food systems, many people hidden from view, many opportunities though to secure those livelihoods, but also to enhance livelihoods through better management. And part of the program, particularly in Africa, has looked at various ways of securing the nutritional values of small fish and the benefits they provide to women, children, and youth. And number 8 is this interdisciplinary approach, and just to encourage cooperation across sectors in health, food and nutrition, energy and water as examples. Again, we traditionally often focus on what's happening within our fisheries and aquaculture departments and ministries and research institutes. But many of the challenges faced and many of the opportunities are there through influencing and working with other sectors. And we have an excellent example from Odisha, where our teams have worked very closely with the women's department, increasingly with the agriculture department, and ensuring that fish is properly integrated into those programs. And in this way, we can ensure that the impacts possible from fish agri-food systems are fully realized through a more integrated, interdisciplinary approach. And moving on to wrapping this up, the statistics are still a challenge for the fish agri-food system. We need to ensure that we have better statistics, better indicators that can be used to monitor, evaluate, and learn how we're making progress towards not just the change and development within the fisheries and aquaculture sectors, but the changes that we can make to the broader food system, food policies, and populations that we work with. And there are multiple agenda opportunities to shift the agenda. This is quite an exciting time. There's increasing recognition of the potential role of fish in sustainable and healthy diets. The Global United Nations Food System Summit is coming. We have a very large effort to promote, enhance the role of aquatic foods within that summit. There are regional, national initiatives related to the UN Food System Summit, and public, private sector, civil society can all play a role in ensuring that many of the often hidden values, the benefits of healthy fish and aquatic agri-food systems are reflected at the highest level. I'll stop there and thank you very much for your attention. And these are some of the global partners that have and are involved with the fish research program, and also recognize the partnership that we do have in India with ICAR and some of the researchers in ICAR, and a special partnership that we do have with the state of Odisha, where we've worked to put some of the sort of high level research into practical use with partners to have real impact on the ground. And that's our objective at the end of the day, to ensure that we work well with partners and that we do, through fish and aquatic food systems, have that impact on the ground that is so important to many people. I'll stop there and thank you very much for your attention, and happy to take questions.
Thank you very much, Dr. Phillips, for your wonderful talk and telling us on the food agri-food systems globally that you have been working with so many agencies for a sustainable development of fisheries and aquaculture to meet the global demand, especially in the developing countries. Thank you very much for that. We would like to take a couple of questions if there are any. Would anyone like to ask any question to Dr. Phillips?
I can see there's a hand up.
There is a hand of Dr. Flowers.
Was that me? That was.
Dr.
So.
Yeah. Okay. Yeah,
Okay.
Professor Flowers.
Yeah, I just wondered if you had any specific initiatives for co-culturing fish and halophytes. I mean, it has been, you know, there've been systems in the past, and present. I just wondered if you have any special initiatives.
Yeah, that's a really good question, and the answer is no, not at the moment. But this is something that we have in our mind, and we have had some partnership discussions with colleagues in the Middle East about the opportunities that there are, particularly in coastal systems, and love to dig deeper into what indeed might be possible there, both perhaps in terms of integrated farming systems, but also, you know, opportunities across the direct consumption, feeds, maintaining water quality. I think there are a whole range of opportunities that could be explored. I know there has been some work already, but I suspect that it's only just scratching the surface there. So happy to take up a longer conversation on that, because I'm sure you have some ideas there as well.
Yes, there's a group called Seawater Solutions who are working in the Mekong in Vietnam, and I think they might be quite interested. So I'll write to you about it.
Can you put your email in the chat? I'll give you a quick,
okay.
Make the connection. Thanks a lot.
Any more questions from anyone? I don't see anyone interested in asking clarifications from Dr. Phillips. It is because, Mike, your talk was so interesting and easy to understand, and thank you very much for that. I think since there are no other questions available, we'll close the session. Dr. Sen, you want to say something?
Yes, on behalf of the organizers, we thank profusely Dr. Gupta and Dr. Phillips for their presence and excellent deliberations and excellent concept that you have been trying to introduce. And the work that you are doing, Dr. Phillips, is remarkable, I should say, for the hungry people all around the globe, for the coastal areas in particular. Thank you very much.
Thank you very much, Dr. Sen. And of course, let's recognize Professor Gupta there, our Nobel World Food Prize laureate. So that was who started a lot of this work. So very pleased to see you today. Honored to be in the same session with you again after several years. So thank you so much.
Yeah, thank you. Seeing Mike, if not physically, but
I know, this virtual world we live in. Okay, thank you, Professor Gupta. Thank you, Dr. Sen. Appreciate the audience today and the opportunity to participate. Thank you so much.
Thank you all, sir.
Thank you, Dr.
Now we're going to close this session. Before that, I'll request all of you that we have started the concurrent session. We all request you, participate. Please. Thank you.
Thank you very much.